All right, and welcome back. So for this, we're actually going to be now tackling the next question. So with that, let me just do a quick screen change, and we should be going on to question number 5. So for this, we have, what is a correct name for copper? And we'll CUS. I can't say the name, unfortunately, because then I'll be giving out the answer. But for this, let's see exactly what we're working with here so we really understand. We have a cation and anion, okay? And to really understand this question, I would actually go first with the anion. We're dealing with sulfur, okay? And sulfur is right here on the periodic table on the 16th column. The reason why we don't want to use the cation, the copper, is it's a transition metal. We can't really say how many electrons it has to give unless we know how many electrons sulfur needs. Because that one is not in transition, it has usually a typical set amount that it wants to take to become a noble gas. In this case, for those in the 16th column, typically want to just have 2 more electrons, so be S2 minus, in order for it to achieve its noble gas state, okay, of filling out its octet. So for it to be S2 minus, okay, so let's actually now break it down like this. We have sulfur, that's 2 minus, so we have, it's going to be -2, and there's just one of them, so it's still going to be 2 minus, well, -2. In order for this to be a neutral, a net charge of 0, we need a certain amount of coppers. We need +2 coppers, okay? But it tells that there's 2 coppers involved. So that means the total amount of the +2 had to be, it's like the total amount had to go up to +2, meaning that every copper had to just be +1, okay? Because that's the only way for it to be Cu2S. You needed 2 coppers of +1 to bond with the S. So that would be Cu plus. Okay, we need 2 of them. So with that being said, what we're going to do here now is see what the name, I guess the chart says about the name. Because copper is a transition metal, the way we identify it is by saying copper, okay, and based on its charge, that we know it's like just +1, it got rid of 1 electron, it'd be a Roman numeral like that, copper 1. And the sulfur would still follow the same rules before, where it would be the sulfur, but you would drop the U and the R and end with IDE instead. So the total name will be copper 1 sulfide. And now let's see what we say here. Do we have any of those type of answers? We have indeed a copper 1 sulfide, but here's the trick: make sure you pick in the one with the Roman numeral. You don't want the one that actually has the 1 there, okay? So in this case, the answer would be B. All right. And that's one of the question. Well, not yet actually. Sorry, I'm getting too ambitious. Let's see what our colleague has to say. If I scroll down, we have the copper is +1, so the correct name is copper 1 sulfide, okay? And they say if the charge was 2+, it'd be copper 2 sulfide, but more importantly, this is what we get, CuS, all right? And we didn't get that, we had Cu2S. So therefore, the correct answers we got was B. So that would be correct. Now let's move on to the next question. Question number 6. Shift it down a little bit. And now they want the names of these following compounds. So we have PCl5, PCl3, Cl2O7, Cl2O3, and NH3, which frankly would most likely be the trickiest one. And I'll tell you why once we get there, but let's start from the top, okay? What do all these 5, so let me just write this down actually, name these compounds So now I'm going to ask you, well, of course you can't answer, but what do all these 5 compounds have in common? They're all non-ionic compounds. As you can see, phosphorus and chlorine, chlorine and oxygen, nitrogen and hydrogen, none of these are ionic compounds. So they do have a certain name rules they'll follow. So similar to ionic, if I just wrote down PCl5, what remains similar is that we would say phosphorus and chlorine, but replace the INE with IDE. Now what's different is that now we have to specify though, because what's the difference between saying PCl5 is phosphorus chloride and then also PCl3 is also phosphorus chloride? For non-ionic compounds, we need to specify the amount of each thing we have. Mostly focus on the second, the anion, I guess, or the second part, the latter half, but we still need to be able to identify how many of each we have. And we use these prefixes to do so. So mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. So we're going to just keep this little cheat sheet in the corner over here because we will be using it. Now, with that being said, PCl5. Like I said earlier, we don't really need to specify the 1 in the front unless it was something other than 1, but we definitely need to specify the part in the back. So that would be penta for this one. So it would be phosphorus pentachloride. And there you have it. Now, if I said PCl3, we would still have phosphorus. We would still have chloride. But now we would have trichloride. So now you can see we've identified 2 different ones. We have PCl5 being phosphorus pentachloride and PCl3 being phosphorus trichloride. So now let's move on to the next one, Cl2O7. We have chlorine and we have oxygen, or better yet, I just like to do this so we can get this memorized. Instead of the oxygen, we have oxide. And there's 7 of them, but there's also 2 chlorines. So we need to do double the work. So it would be dichlorine, and then here 7, hepta, or I guess you drop the A sometimes. That's the part I'm never too sure about, but I'm just going to put the whole thing, dichlorine. I'm going to drop the A for it because it's followed by a vowel, so it'll be heptoxide. Dichlorine heptoxide. So now we have Cl2O3. And now we have Cl2O3. Same chlorine, same oxide, but now we have dichlorine trioxide, and this time we do keep the I. So we dichlorine trioxide there. And now for what I believe is the trickiest one, NH3. The reason being because we were not, I mean, we technically could say nitrogen and then hydride, and then we could say trihydride, but nitrogen actually has a more common name that we refer to all the time, and that would be ammonia. Unfortunately, this is one of those that you just have to memorize, because how you can get nitrogen trihydride from this, beats me, but we do know is like the common name we have for it is ammonia, and that's what we're going to call it. So with that being said, let's see if my colleague agrees. So we have phosphorus pentachloride, perfect. Phosphorus trichloride, dichlorine heptoxide, perfect. Dichlorine trioxide, and then we have ammonia, which is exactly what we got. So we are good to go. So now for question number 7. For 7 we have the value of Kb is 4.30 times 10 to the negative 4. And now they want us to write the equation for the reaction that goes with this equilibrium constant. So with that being said, what they really want us to do is understand what it means for it to be Kb. Kb is the, I guess, association constant. Because instead of dissociating, it would be more so the constant at which this base, ethylamine, takes a proton from its environment. So the formula we actually we're working with is going to be C2H5, and H2, okay? And it looks something like ethylamine would probably look like that, and then it has the hydrogens on it. So more, instead of having to draw the hydrogens, this would probably be what it looks like, and that would be ethylamine, something like that. But the point being is that this nitrogen, this lone pair, is actually what's going to be the part where when a proton comes in, okay, is going to go onto this lone pair. So what's going to happen here with this equation is going to be plus H2O, all right, and just can't forget your units. Well, I guess the aqueous, liquid, and then we have the formula. And like I said, even though it has hydrogens in it, what's happening here is the nitrogen is taking an extra 1. So it would be C2H5 and H3 plus. This would be its conjugate acid, and it will be plus OH minus. This would be what's actually happening here. This would be for the Kb, because Kb needs the base, the acid, the conjugate acid, and its conjugate base. Now the part we have to realize is that for the Kb, it is products of reactants just like Ka. The key difference here though, alright, is that we do not include water because it is the solute, the solvent, not the solute. We don't include the solvent typically because it's just what everything is in anyways. So for this, actually, if we have products, the concentration of products over the concentration of reactants for Kb, we're going to have Kb is equal to C2H5 and H3 plus right here, plus the OH, well not plus, multiply with the OH minus over just the concentration of C2H5 and H2. And because we actually knew what the Kb was, I'm going to copy and paste this here actually. We can actually now rewrite this to where, in a theoretical sense, 4.30 times 10 to the negative 4 is equal to these concentrations like that. And this would indeed be the equation that would go with this equilibrium constant. Now let's see how we did. So exactly, we don't really need the other information whether it's a weak base or weak acid. But yes, it is a weak base. The reason why I was able to say that because they gave us the Kb and they gave us its basic form. And I think the one part I do want to emphasize is that the reason why I drew this picture here in this corner is that you do have to understand the structure of what you're working with, or at least recognize groups. This C2H5NH2 has an amine group, the NH2, which is why I was able to quickly point out that that will be where it takes a proton from its environment, hence how I could draw with much more ease its conjugate acid. But just like our colleague, we have the Kb is 4.30 times 10 to the negative 4, which is equal to the products over reactants. And this would be correct. And now for question number 8. So for this one, we have the 4 bonds of carbon tetrachloride are polar, but the molecule is non-polar because the bond polarity is cancelled by the symmetric tetrahedral shape, which is true. When other atoms are substituted for some of the chlorine atoms, the symmetry is broken and the molecule becomes polar, which is also true. Now I want to rank the following molecules from least polar to the most polar. Okay, so this is where it's going to get a little bit tricky. We want to make sure that we understand the gravity of the electronegativity difference in order to rank these properly. So we have for the first one, so rank the following, okay? Let's see here. We have CH2BR2, CF2Cl2, CH2Cl2, CBr4, and CF2Br2. Okay, so with this, I've drawn out all 6 of them, which I have. Perfect. So now the way I would do this actually is because the carbon is going to be kind of like a null variable. There's always going to be, I guess, carbon in the middle. What I actually want to find out is the electronegativity difference between the hydrogens and the bromines in this first case. Why? Because if I was to quickly draw a quick sketch, this is what we have. H, Br, Br. So if I find a difference in electronegativity between like this part or this part, it doesn't matter what you choose. Point being is that you want to, or even like it would be this part here, for example. The reason why we have to do that is just because we can then see how much of a electron distribution would it actually be. Like how much of it would it prefer to go to bromine if, for example, the hydrogen is not doing its part. So with that being said, let's go to the periodic table. Bromine has an electronegativity of 2.96 and hydrogen is 2.20. So that's 2.96 minus 2.20 and we get 0.76. So the difference here is 0.76 electronegativity. Now for the next one, same concept, draw a quick sketch. I actually don't draw a quick sketch for each one. So it'd be F, Cl, Cl, and it'd be H, Cl, Cl. And this one, I think we already know what's going to happen here because it has all BRs. And then, were there 5 or 6? Maybe I miscount. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I'm definitely missing one of them. CH2Br2, CF2Cl2, CH2. Oh, I missed the CH2Cf2. So CH2F2. That's the last one. And so now with this, we have F, Br, Br, and then we have F, H. Okay, perfect. So now the same concept, the electronegativity difference, like, you know, between, I can even say between these two. Same concept here. Doesn't matter what I pick as long as I'm picking two different things. So back to periodic table. Chlorine is 3.16 and fluorine is 3.98. Minus 3.16, we get 0.82 difference. Okay, now between chlorine and hydrogens, we have 3.16 for chlorine and 2.20 for hydrogen, and we get 0.96. Now between the bromines, it doesn't matter what we circle here. So this one could have been like that. Bromine does not matter what combination we circle, we just end up with 0 because all the bromines cancel out. Just like how the CCl4, the bonds are polar, but it was non-polar. This is the reason why, because the difference between them is always going to be 0. Now we have the bromines and the fluorines. That'd be 3.98 minus 2.96. And we get 1.02. And then for the last one, the fluorines and the hydrogens, we get 3.98 minus 2.20. And we get a whopping 1.78. So with that being said, they want us to rank it from the least polar to most polar. So with that, CBr4 will be our least, according to this list. So we're done with that. And then next up would be the 0.76. So CH2Br2. Then the next up would be the 0.82, which would be CF2Cl2. And then next up would be the 0.96, which is a CH2Cl2. And then CF2Br2, and then the last one, CH2F2. And now with that being said, let's see how we did compared to our colleague. And they did order it for us. And let's see here for the differences. And they do get CBr4, CF2. Oh, that's interesting. Why would they put CF2Cl2 so high instead of the CH2Br2? Let me just double check. Bigger electronegativity. Let me see here. In the CH2, the carbon and hydrogen dipole moments have the reverse polarity. Therefore, instead of contracting the dipole moment, they strengthen them. Oh, because the hydrogen is so low, it actually goes lower than the carbon. So it serves as actually like a stepping stone for it. So if we actually were to now modify that based on that, if we looked at every hydrogen own, we would actually, so in that case, that was my fault. We would actually look at the carbons, because the difference between carbon and hydrogen, it's a positive 2.20 minus, well, 2.55 minus 2.20. So that'd be 0.35. And that would be what you would add in because of the fact that carbon is actually trying to take electrons from the hydrogen. Although it's totally non-polar, like by total, because the difference isn't that great, it will still contribute to the electrons wanting to be on the boron side. So we 0.76 plus 0.035, and we get 0.35, sorry, and we get 1.11. So actually 1.11. And then not, this one wouldn't count because the chlorine and the fluorine are both greater than the carbon. Here, same thing, actually we adding the 0.35. So that would be 1.31. And then here is still 0. Here the bromine and the chlorines are both quite high compared to the carbon. I mean the bromine and the fluorines, so that one doesn't change. And then here the last one, although it's still already 1, we still add the 0.35, and we get 1.78 plus 0.35, 2.13. So that would be the key thing here, actually, that I do apologize for not going over, is that the carbons do play a role when their electronegativity is greater than their surroundings. Because typically, the surroundings are typically greater than the carbon. Like the fluorine, chlorine, and bromine all have electronegativities greater than the carbon. But hydrogen does not, which is why that's where it changes. So with these new revised numbers, it would actually be, so CBr4 is last, then it would indeed be the CF2Cl2. Because that one's the next one at 0.82. Alright? And then after, the lowest one is 1.02, which is a CF2Br2. So that one goes here. And then the next one is a 1.11, which is a CH2Br2. And then we have the 1.31 is CH2Cl2. And the last one still remains CH2F2. So with this, hopefully, at least based on what they're showing me, that's my reasoning. Let's see how we're actually now able to do. So exactly, CBr4, perfect. CF2Cl2, perfect. CF2Br2, awesome. CH2Br2, awesome. CH2Cl2, nice. And the CH2F2. So exactly, let me actually go ahead and circle the ones with the carbons and the hydrogens. So like these two, well, technically these three were the ones that were greatly impacted by the fact that it was sorry, I circled the wrong one. It was a carbon hydrogen bond in it, which added to the electronegativity difference, rather than the other ones, which we have to just ignore it because carbon was the lowest one. So that is what's happening there. So that this is correct. And now let's move on to the next question. Question number 9. So question 9 we have, how is the ranking of the following compounds according to their boiling point? So we have M-hexanol, which if I remember correctly would be like something like this. I'm not really sure what hexanol is. It's a specific type of group. Just trying to remember it clearly because ANAL would be, I believe, a type of ether. No, that wouldn't be it. Hexanol, let me actually use my colleague here. That's what it would be. So it would be a double bond. So this would be sorry, it has a not a ketone group. This would be a aldehyde, I believe, because it's at the end. 1, 2, 3, 4, 5, and exactly we have the double bond oxygen for hexanol, and hexanoic acid would be 2, 3, 1, 2, 3, 4, 5 again, and OH, and then the O again. And for hexane, it'd be just the 1, 2, 3, 4, 5, 6. Sorry, too many. 1, 2, 3, 4, 5 for hexane, and 1 hexanol would be just same thing really, but 1, 2, 3, 4, 5. But instead, it would be just like that. Okay. So we want to rank this according to their boiling point. For this, the way I like to do it is that we have to remember that for one, the one with no types of groups, no groups in it, just a hexane, this is the lowest boiling point. We'll just say it's 1. Lowest boiling point. It will be, in fact, if we label these A, B, C, and D, we know that C has the lowest boiling point compared to everything else. Now, what I like to do is because we do know that oxygen carbon bonds, CO bonds, do require more energy to break. So that's definitely a place to start. But what I actually like to do is focus on the hydrogen bonds. Which one of these, now that we've gotten rid of C, we've already said it's the lowest because it has no functional groups. Which one of these has hydrogen bonds? D and B. Okay? A does not. With that being said, hydrogen bonds, like OH bonds, require a lot more energy to break. So with that being said, A would have to be the next one, considering that B and D have hydrogen bonds. And now this is the way you differentiate between B and D. B has a hydrogen bond and a CO bond, while D does not. Because of that, it would be D, and then B would be the compound that has the highest boiling point, which makes sense because typically speaking, carboxylic acids usually have the greatest boiling point, considering that they have a hydrogen bond along with a carbon oxygen bond as well. But depending on the molecule, just to make sure you watch out for those things, and you should be able to pinpoint the one that would take the most energy to boil, which just translates to breaking their bonds. So with that being said, let's see here what our colleague has to say. So hexanol, as they said, was this shape. I believe this is known as either a ketone or an aldehyde. I do want to say aldehyde because it has the oxygen at the end, and ketones usually have the oxygens like in the middle. Then we have a hexanoic acid, which is what we're able to draw. Perfect. We have hexanol, which is also what we're able to draw. And we have hexane, which is just nothing, like I said. Okay? So the compounds here, as they said, there was an alkane, an aldehyde. Oh, it is an aldehyde. Nice. An alcohol, and a carboxylic acid. And the main factor here is intermolecular forces. We want to now see exactly which type of bonds will be the hardest to break. So the ranking would be, as they said, because alcohol has a hydrogen bond, it has an OH group, it's placed high up there. And aldehyde just has an oxygen atom that interacts with other hydrogen atoms, but the point being is it's just a CO bond. So that is why it would indeed be hexane, followed by the hexanol, which is the A, and then 1-hexanol, which is the OL, the alcohol, and then hexanoic acid would be the strongest one. So this will be correct. And now for question number 10, we have, what is a systematic name for MgNO32, NH4ClO3, and PbO, and how do you get those answers? So the common thing among these, if I just were to quickly write them out, MgNO3, and unfortunately we do see the first two answers, and I cannot stop that. MgNO32 and NH4ClO3 and PbO. The thing that all these three have in common, if you refer back to the periodic table, is that theoretically you should have a cation and an anion. All of these should be, I mean, that's also what we have for even non-ionic, but point being, I actually want to stress that these should all be theoretically ionic compounds. Even the NH4ClO3, just because ammonium ions do kind of work as the quote-unquote metal in these cases. And the last one we have is PbO, which is lead. And lead is technically a metal, well, specifically it's a post-transition metal. So that's why all these should theoretically be, I guess, pseudo, at least, ionic compounds. So they do have their own type of naming, alright? So with this, we just have to start out straightforward. We just want to write down the cations of each. Magnesium, ammonium, and lead. Now, I do want to stress, though, that the way I got ammonium, I did memorize those. You do have to memorize them because if you take a glance at NH4, there's no real way, at least for me, to think about what to name it unless I memorize just that NH4 is ammonium and NH3 is ammonia. with that being said, kind of the same approach here of now getting the anions. We have NO3. I know this because I've memorized them, like the 8s. All right, we have nitrate, chlorate, phosphate, sulfate. All these 8s, we have to make sure that we are naming it right because NO3. So we need 3 oxygens, which is what this has. That would be nitrate. So we can actually say magnesium nitrate. And the cool thing about nitrate is that nitrate is known as NO3 minus. And if magnesium, being on the second column, likes to give up 2 electrons to achieve its noble gas state, nitrate, there needs to be 2 of them to balance it out. Hence why we have MgNO3 2. Now ammonium, okay, NH4, we have, it's just going to be a plus for the whole thing. Alright, and chlorate, ClO3 minus, that's what's known as. Funny enough, make sure for one you have 3 oxygens there, which is what you do, so you can call it chlorate. It's just 1 minus. Hence how it balances out 1 to 1, and we can just call this ammonium chlorate. Alright, and now for the last one. This is where it gets extremely tricky. Well, yes, it gets tricky. We have lead oxygen, but just like renaming the, when it comes to the metals as the anions, it would be lead oxide. But we're not done here just yet. Oxygen is not a transition metal, it's just a reactive nonmetal, but lead is a post-transition metals, and even these ones have different types of ions it can make. With that being said, we have to specify what type of lead we're dealing with. It was a 1-to-1 ratio, and oxygen is known for gaining 2 electrons to achieve its noble gas state. So we have O2 minus. So the lead, for it to be 1-to-1, has to be 2 plus. And if lead is 2 plus, we need to specify that in the name by writing the Roman numeral 2 next to it. And that would be what you get for this. It would be lead 2 oxide. Alright, so let's see what our colleague has to say. MgNO3 is indeed magnesium nitrate. That's perfect. And they do balance it out. NH4ClO3 is ammonium chlorate. Awesome. And lead PbO is indeed lead 2 oxide, because we needed O2 minus, and the only way for lead to go 1-to-1 ratio, it needed to be 2 plus. So, and just like how it says here, which is important, this ion sometimes exists with a +3 charge, meaning that we sometimes have Pb that's 3 plus. If that was the case, we would actually end up with Pb2O3, and this one we'd call lead 3 oxide. So these are just the small things to watch out for, especially when dealing with transition metals, because you want to be able to specify what type of ion you have there. So that will be it for question 10, and now for number 11. For number 11, we have which type of bond exists in each compound. So we have quite an extensive list here. Yep, yes we do. And we're going to start from the top. So type of bond. Alright, and the first one we have is KCl. So what is KCl? This is potassium chloride. So it's really just a potassium that's given up its electron, so it's a potassium ion, and a chlorine that's taken that electron, and we have this really. And as I've said, 2 ions, a metal and a non-metal, and we know this as an ionic bond. So this would be B, an ionic bond for this case. Make sure you pay attention to your A, B's, and C's, because it looks like it changes for every question. So that's why I actually even wrote ionic next to it, just so you can verify. BCl3. Next we look at our periodic table again. Boron is known as a metalloid. Okay? And chlorine is definitely a nonmetal. So, here is where the gray line is always drawn. Metalloids, are they metals? Not so sure. So instead, I would refer by its electronegativity. The reason why we didn't really have to do that for the potassium is potassium is definitely a metal. But the electronegativity cutoff, if you're curious for ions, and not ions, for ionic compounds. So chlorine was 3.16, potassium is 0.82. The cutoff is actually typically at least greater than 2. Or if you really want to skate next to the line, if you're at least greater than 1.6 electronegativity difference, and it's a metal with a non-metal, you can say it's an ionic compound as well. But BCl3, this one is kind of looking more like they're kind of sharing it. The reason why I'm saying they're sharing it is because now, if we referred to the electronegativity, boron would be 2.04, chlorine is 3.16. The difference is only 1.12. So, although it passes the cutoff for a polar covalence, because for non-polar covalent it has to be less than 0.4. That's typically just the rules that were given. It definitely passes a polar covalent, but it's not enough to say it's an ionic compound or ionic bonds. So with that being said, I would say that this would also be B for polar covalence. And there we have it as an example of, it does have the word metal in it. It's a metalloid, but to be on the safe side, I would refer to the electronegativity difference. And you can see here that because it's not so big, it would be safer to say that this is a polar covalent bond. P4. So this one is just phosphorus with itself. So with that, I don't really need to even draw a picture. I don't even know if I can. But the point being that because they're all phosphoruses, for one, it's definitely not going to be a metal and a metal together. But two, more importantly, the electronegativity difference will be 0 because all the phosphoruses have the same electronegativity. So if it's 0, that definitely doesn't even pass the cutoff of 0.4, making this A, which is going to be non-polar covalent. And now, that'll be it for this one. BR2. Funny enough, same concept here. But let's see what letter we're dealing with. In this case, it will be C, but C would also be non-polar covalent. And now we have CO, carbon oxygen, carbon monoxide. For this one, it would kind of look something like this. Not sure how to draw it. Probably not the case at all because carbon needs to, it'll be more like this. Worst case scenario, where the carbon now is very negative and the oxygen is very positive, but that's the only way really for it to stabilize. With that being said though, just double checking, what we want to know is the difference in electronegativity. So back to our handy periodic table, we have carbon 2.55, oxygen 3.44. So it doesn't go all the way to an ionic compound, which is what we expect because these are not, neither of these are metals, but it definitely passes the cutoff for a polar bond. So with that being said, CO would be polar covalent, which is A. Polar covalent. And now SO2, the last one for this one, we have sulfur, well, kind of oxygen, sulfur, oxygen. Now this one's a little bit tricky because it's asking for a, let me check here. The question is asking for is what type of bond exists in each compound. So it's not asking for whether the whole molecule is polar or non-polar. It's asking for the type of bond there. Because I would say this molecule in total is non-polar since the oxygens are pulling both sides equally. But the difference now is the bond itself we have to see. Oxygen is 3.44, sulfur is 2.58. So 3.44 minus 2.58, we get 0.86. So with that being said, let me see here. It definitely passes the cutoff for a for it to be at least polar. But exactly, we have in this case it would be C for polar covalent bonds. The key thing you have to remember though is that yes, SO2 would still be a non-polar molecule because these polar covalent bonds cancel each other out. So with that being said, let's see what they got. So we have B is ionic, that is correct. BCl3, polar covalent bonds, perfect. P4, non-polar covalent. Br2, also non-polar covalent. CO, polar covalent. And SO2 is polar covalent. So, with that being said, all of these are correct. And now let's go on to question number 12. For question 12, we have the equation for the combustion of butane, C4H10. Alright, is that plus 13.02. So I'm actually going to write this all out. Plus 13 over 2. This is another way to write this, the O2 down, because it's pretty much saying that we have 13 oxygens instead of saying 6.5 O2. And this turns into 4 CO2 plus 5 H2O. And actually, let me check. 13 over 2 oxygens actually be 13 oxygens. I do apologize. Not 6.5. It'd be 6.5 O2, which is just 13 oxygens. I'm not sure what I said earlier. I just want to clarify that, which makes sense because 4 CO2 is 8 oxygens in total plus 5 oxygens, and that is indeed 13. So, which of the following generates the least heat? So what this question is asking really is which of the following is the smallest amount of moles being used or produced? Okay, so the first one, A, says burning 1 mole of butane. So I'm just going to make a whole list for each, I guess, situation. So for A, burning 1 mole of butane, we have 1, 13 over 2 here, 4 here, and 5 there. Those are the number of moles it's working with to burn 1 mole of butane. And now if we want to react 1 mole of oxygen with excess butane, what we now have is 1 here. Based on this ratio, it would be 1 divided by 13 over 2 for how much you would use. And in that, we would have, 1 divided by 13 over 2. We want to make sure that 1 divided by 13 divided by 2. Okay, there we go. So let me just double check here. 2 over 13 is what we get. All right, that's how much of that we have. And then multiply that by 4, that'd be 8 over 13. And then for here, 2 times 5, that'd be 10 over 13. So we have gotten a lot smaller in terms of what we're working with. So this is definitely a good start. All I'm doing now is pretty much comparing the ratios of each based on what was given. And the next one says producing 1 mole of CO2. So that'd be 4 instead of 1, right? So everything here is divided by 4. So it'll be 1/4 of this. And 13 over 2 divided by 4 would be 13 over 8 of that. And then the 5 divided by 4 will be 5/4 of that. And now for the last one, 1 mole of water, we have 1 mole there, so it'll be 4 over 5 now. And then for this one, it will be 13 over 10. And for the last one, it will be 1 over 5. So these are all the ratios we have. For this, it'd be the best and the easiest to pick the simplest one. I think the C4H10 row is relatively easy to work with. So that's what we're going to use here. And I'm going to see which one of these is the smallest number. So 2 over 13 is 0.15. 1 over 4 is 2.25. And 1 over 5 is 0.2. So in this case here, the smallest one we're working with is actually this row, which is when we were reacting 1 mole of oxygen with excess butane. So with that being said, B will be the correct answer because it produces the least, I guess, fractions ratios of every mole. So they got the equation, and then they did burning 1 mole, and then they compared it in a sense with like a Q. That's where they attributed it. And then they said the heat generated by 1 mole of oxygen with excess butane is 1. And producing 1 mole of carbon is 1/4 Q. And they rewrote, I think they wrote this part a little bit wrong. Because it should not be 1, it shouldn't be 1, it should be 2 over 13 Q. And then we have 1/4 Q and 1/5 Q. And from this, we can see that reacting 1 mole of oxygen with excess butane generates the least heat, which would be the letter B. So he's like 2 over 13. That's actually what I wanted to find. 2 over 13 would be times that Q. 2 over 13 Q. So with that being said, though, although slightly different approach, this is also correct. And now we can move on to the next question. Question number 13. So for 13 we have, which of the following is not produced through chemical bonding? So not produced through chemical bonding. So for this one, this is a kind of a tricky conceptual question because we first need to understand what's being asked. Okay, so for this, if I rephrase this and said, what are all things made of? Matter. But what does matter consist of? If we went down to our molecular level, we're now dealing with molecules. So cells, and the reason why I say molecular level is because those molecules are made through chemical bonding. To get a molecule, you need a bond. So just like H2O, this is a molecule, for example. Now, if we say cells, the heart, atoms, and adipose tissue, which one of these is not made of molecules? Funny enough, the only one will be atoms, because atoms are not bonded together. So in this case, the answer would really just be C. And the reason why they're not produced through chemical bonding is because they are atoms. They don't have any bond. It's like another way to ask this is if I were to say, if it has sodium, right? Did I make this through chemical bonding? What did I put together to create sodium? Sodium is just an atom by itself. There is no bonding involved. It's not sodium with it's just sodium, a sodium particle, a sodium atom. That is what they mean here, because as we know, cells are made of, I think they're called organelles, and organelles have different proteins and stuff in them, and proteins are molecules, and molecules are made of atoms. Same thing with the heart. Heart's made of cells. Back to the point again. And adipose tissue fats. Fats are made of triglycerides and stuff. Those are molecules, and molecules are also made of atoms. So all of these are made of atoms, but atoms are just atoms. They don't need any bonds. They don't have any bonds, actually. That would be what an atom is called. So that being said, exactly. Atoms are the smallest unit of matter, and it has no bonds with it. So this is correct. Now with that, we're going to actually pause here before we get to question number 14. Take a mini break here. I will be right. Let me just switch over to here first. So exactly, we're going to take a small break, and I will be right back.